And I'll pass it over to Wilbert.
Great, thanks, Hazel. And if everybody, please would like to introduce themselves in the chat, that would be good. So welcome. This is the session from the IARPIC Modelers Community of Practice. So IARPIC is the Interagency Arctic Research Policy Committee. It brings together leaders from many agencies, departments, and offices across the U.S. federal government to enhance collaboration on research in the Arctic. The Modelers Community of Practice aims to enhance understanding of the integrated Arctic system through the use of regional and global system models. Today's topic is tipping points. As the Earth system is warming, there is an increasing risk that thresholds will be crossed that will lead to abrupt and possibly irreversible changes. The high-latitude Earth system in particular contains powerful feedbacks that could give rise to such tipping points, for instance, associated with the ice sheets, sea ice, or the large-scale ocean circulation. 2 months ago, in the previous Modelers session, Ricardo Winkelmann and Betty Otter-Bliesner presented on the large international projects, TIPMIP and What If MIP. But today we'll stay a little bit closer to home. We'll hear from 2 U.S. science leaders about their efforts to explore tipping points in the high-latitude Earth system. So we have 2 presenters today, and we'll start with Natasha Romanow. She's a research scientist at NASA GIS and an adjunct associate professor at Columbia University in New York. And she has a PhD in physical-oceanography from Florida State University. And she's going to talk about fingerprints of AMOC collapse in the Arctic Ocean.
Okay, thank you very much. Thank you, Wilbert. Thank you, everyone, for inviting me in this series of talks. I will start by sharing my screen. Yes, and as it was said, I'm Anastasia Romanow, Natasha Romanow, and I will be talking about Arctic fingerprints of an AMOC collapse case that we have in our model simulations. I represent here the NASA Goddard Institute for Space Studies, which is nowadays a virtual institute since we are evicted from our 60 years, the building that we were for the last 60 years. And this work is in collaboration with colleagues from NASA GIS, David Rind and George Eliudis, and Paul Lerner from Columbia University. And of course, it is based on the work that the entire modeling team is doing to put together the NASA GIS Earth system model, including oceans, atmosphere, ice, vegetation, and carbon cycle. So first of all, I'll give an overview of my talk, which is about the state dependence of the AMOC impacts. This is a notion that we have implicitly known for a while, but recently is becoming more, coming more into focus. Then I will talk about AMOC bifurcation that we identified in our SSP 4.5 scenario. And then I will talk about fingerprints. I was initially asked to give a talk about impacts of the AMOC, but it's very hard to separate what is an impact and what is a fingerprint, meaning a coincidental situation that is happening as the AMOC collapses or has collapsed, and not necessarily that it is an outcome of this AMOC collapse. Nevertheless, fingerprints are very important and are studied more and more recently as proxies to AMOC collapse. Surface, I will discuss surface fingerprints, water cycle fingerprints, Arctic water masses and strait transports, sea level rise, carbon cycle and marine ecosystems, and Arctic marine ecosystems, marine extremes. Okay, so as I said, the state dependence of the AMOC collapse has been in our mind in the scientists' mind for a while. We understand that it's a different thing, AMOC to collapse in a pre-industrial climate versus in a warmer world like we are today, or even in an even warmer world in the future if we continue emitting as the amounts of CO2 we do right now. However, a recent study brought this into very good focus. They did the hosing experiments, is a study by Lomo and Melling 2024. They did hosing experiments in an Earth system model and looked in 2 different configurations, one in a pre-industrial climate and one in a 4 times CO2 climate. And they found that while the impacts or the effects of the AMOC collapse in the system, like the cooling and the precipitation changes that you can see here in the figure, have the same regional distribution, the magnitude is quite different. And if someone digs more into details in other parts of the system, then some of the effects might be quite different. So here it shows, for example, that in a 4 times, the upper panels show that in a 4 times CO2 world, an AMOC collapse will result in a smaller, weaker cooling in the North Atlantic, and also weaker changes in the precipitation in the North Atlantic. So this needs to be borne in mind. And I repeat again that these were housing experiments, meaning that they input large amounts of fresh water into the system in order to get the AMOC to collapse in both cases. Here, I'm going to discuss about simulations using the NASA GIS Model E, which for the two 4.5 extended scenarios, CMIP6 extended scenario shown here, where the forcing of CO2, the concentrations in the atmosphere increase linearly to 2100, but then after that, the increase slows down and then even starts to decline. This is the extended scenario. We did this scenario with 10 ensemble members, and we found that something which is quite unique, it's not, to my knowledge, it has not been seen in Earth system models before. We saw that 8 of the 10 models exhibited an AMOC that recovered after 2200, more or less. After 100 years of the turn of the slowdown of the forcing, whereas 2 of the ensemble members continued to decline and came to a stop. This is AMOC in this figure, AMOC with time at 26 north, and here is AMOC at 48 north, which shows complete shutdown of the subpolar gyre. Now, why this is important, it is because we have no hosing in the simulation. We didn't add any external freshwater input. What happened is that in our model, the active area of deep convection shuts down because there are extreme events of sea ice mass flux coming through the Denmark Straits that you can see down on the bottom left figure. This area here, which is the active convection, Labrador Sea is frozen over and doesn't convect since the 2100. But later in the simulation, only the Irminger Sea remains active. The convection remains active, and it will shut down in the cases where extreme events of sea ice transport will bring sea ice into this area, which will melt and stratify the ocean and stop convection. And you can see here the sea ice mass transport across the Denmark Strait, and you see that in the 8 ensemble members, this flux actually declines with time, but in these 2 simulations keeps growing with time as aided by feedbacks from the atmosphere and the cooling, and so the mixing stops. So in the following figures, I'm going to be showing differences between parts of the system, different fields of the Earth system. Differences between averaged over the period 2350 to 2400 from the scenarios that collapse minus the scenarios that the AMOC recovers. And I will call this as fingerprints of an AMOC collapse. And I will start, of course, with sea ice coverage. Sea ice is critical in this area because it connects essentially the impacts of the AMOC collapse to the atmosphere and plays a big role at setting the response of the system in the North Atlantic, the subpolar North Atlantic. In the AMOC on case, I will distinguish the AMOC on case and the AMOC off case. In the AMOC on case, the ice contracts, sea ice contracts, Whereas in the AMOC off case, the sea ice now expands. It covers essentially a big part of the Greenland, Iceland, the Gene Seas, and also hugs around the Greenland. Now, such sea ice distributions, of course, cool the surface air, make it denser. Here is a description of the surface air temperature. Surface air temperature is much cooler in the collapsed case than in the AMOC on case. And that difference in temperature, which is about 2 to 5 degrees, extends all the way south to Central Europe. Now, this colder and denser air will, of course, impact higher surface pressure, means higher surface pressure, and higher surface pressure means fewer storms. So you can see here that the Icelandic low, that is quite pronounced in the AMOC on case, in the AMOC off case has greatly reduced. Storms now are moving more to the south, being pushed back by this surface cooling and increased pressure at the surface. Looking at the impacts of the AMOC shutdown in the water cycle, meaning the precipitation, evaporation, and the surface ocean salinity, we see that the AMOC off case is associated with decreased precipitation, quite significantly decreased precipitation in the Gene Seas. Now, you will see that a lot of the changes that are impacted in the region are much more pronounced in the subpolar gyre, which is the area where immediately feels the impact of the shutdown of the AMOC. The AMOC, the overturning circulation will not allow the North Atlantic current to reach further up north and enter the subpolar gyre and then warm up the area and also bring in more salt. And so the transport of this, the reduced transport, or the so-called salt advection feedback that we have in the subpolar gyre is obviously more pronounced in the Gene Seas, but the impact of it is felt in the southern and eastern edges of the Arctic Ocean through the transport through the straits, but also through, of course, exchanges with the atmosphere. So the precipitation is much lower in the case where the AMOC is off. And of course, that makes sense because the colder air holds less moisture. And less moisture will also mean less evaporation. And we see the evaporation here greatly reduced compared to the evaporation in the AMOC on case. Whereas the middle of the Arctic Ocean is maybe not so much impacted by this evaporation changes. Remember, of course, that it is all covered by substantial sea ice. Now, less evaporation and less precipitation mean that there will be a lower salinity, surface salinity. Now, surface salinity is also affected critically by transport of the water masses, and the water masses that come in from the south, again, are much lower salinity. But of course, the E-P will reinforce this deficit of the salinity. Now, as we moving forward, this deficit of the salinity in the subpolar gyre will eventually translate into a new kind of Atlantification of the Arctic Ocean. Here we are looking at vertical sections of temperature, salinity, and density across the Bering North Pole Gene Seas transect through the Arctic Ocean. On each plot, on the left-hand side, you see the AMOC on case, and then on the right-hand side, you see the AMOC off case. Here, in every plot, the first basin is the Gene Seas. You see it much more stratified in the AMOC on case, much warmer and salty waters. And of course, quite dense. But as we move into the Arctic Ocean, of course, is characterized by the typical water masses that we find in the Arctic Ocean, the polar mixed layer, fresh and cold waters. Near the surface, below that, the Arctic halocline, which is very important, and later on the Atlantic water that comes in from the Atlantic, which has some stratification. It's warmer and saltier, and then of course, and at the end we have the deep water masses in Arctic deep water masses. In the AMOC off case, the genesis has changed substantially. You can see here that the stratification is increased, but it is characterized by colder and saltier waters. And these are the waters, and also at the surface you have a much colder layer of waters, which is the due to the sea ice, the presence of sea ice. Now this, however, Atlantic water will make it into the Arctic Ocean through the Fram Straits and the Barents Sea area. And then you can see that the impact of the water that comes in from the from GNCs will ultimately change substantially the stratification in the Arctic Ocean. The polar mixed layer extends and sort of takes over the Arctic, merges with the Arctic halocline, and we have much higher stratification in the top, which helps maintain these large amounts of sea ice that have been building up at the surface due to the warming hole. Below the stratification, the salinity as well, below that surface layer, the salinity also is very stratified and mirrors very well what happens in the GNCs. And of course, as before, density will follow the stratification profile because it's salinity is much more important for density in the Arctic Ocean. So we see here a reverse Atlantification. Usually we associate Atlantification with the input of waters, like warm and salty waters that come from the Atlantic, from the subpolar gyre into the Arctic Ocean. But here we have again Atlantification, but it's a different kind because it's colder and fresher waters. Now, all this fresh and cold water that ends up into the Arctic Ocean, one would expect that due to the thermosteric effect would cause contraction, right? We have colder waters, therefore the sea level should drop because of the thermosteric effect. And indeed, if we calculate the thermosteric component of the sea level rise in the Arctic Ocean, we will find it negative, meaning that it drops. However, the halosteric effect, the sheer amounts of large freshwater fluxes that we are putting into the surface ocean, the freshwater, lead to a halosteric effect, which is quite large and ends up giving sea level rise of about 0.5 to 0.8 meters in the Arctic Ocean, and in particular in areas closer to all around Greenland, and less so, although significantly, in the northwestern Europe. And again, this is due to the halosteric effect, which for the rest of the globe is kind of insignificant, is very small. But in the area of the Arctic, because we have these large amounts of freshwater input into the system, freshwater for about 200 years, because remember, we are looking at the differences between the states of the AMOC on and AMOC off case 200 years after the AMOC has declined substantially. So this halosteric effect adds up to cause such large positive increases of the sea level rise in the Arctic Ocean. And of course, because we are using a coupled air system model where we have a carbon cycle active both on land and the ocean, here I'm only looking at the ocean, we are able to look at what are the effects are of the AMOC shutdown on the primary production and also in the carbon uptake. The North Atlantic is very well known for the North Atlantic bloom, which is a big productivity spike that lasts for several months every year, promoted by the upwelling of nutrient-rich waters from depth, the area where of interest, the area where the deep convection and water mass formation is an area where nutrients upwell and they become available to ecosystems at the surface of the ocean, and those proliferate. And we see primary production increases due to this effect. However, when the AMOC shuts down, nutrient availability becomes much more reduced, and therefore primary production becomes very small, very little, and in fact it is almost zero in the critical region south of Greenland. Again, this area is the area where the AMOC changes, the AMOC subducts, the surface water subduct and produce the North Atlantic deep water is the area where we take the system the ocean takes up carbon and takes substantial amounts of carbon, alleviating some of the climate change that we are experiencing, some of the global warming that we're experiencing. And we see that this area, again, which is an area of an intensive sink of carbon, becomes a much weaker sink of carbon in the when the AMOC collapses. And that is associated with the fact that we have, again, stratification, this shutdown of the AMOC, stops the convection, and of course stops the upwelling of the mixing up of carbon-rich waters that can take up more CO2 from the atmosphere. Now, we have also been able to look at marine heat waves and extreme acidification events in the ocean in these two cases of AMOC on and AMOC off runs. And we look at here the marine heat wave intensity and extreme acidification. Both extremes are calculated using the Hobday method, meaning that we are looking at deviations above a local climatology. And the local climatology is of the late historical, 1980s to 2014 in our model. And we see that in an AMOC on case, of course, we have, because of the warming, we have extensive heat waves in the North Atlantic that reach maybe even 3 to 4 degrees C above the climatology. But in the AMOC off case, all these, of course, extremes, heat wave extremes, disappear. And they disappear here because obviously we have very cold temperatures at the surface. A big part of the ocean is covered by sea ice. That doesn't mean that further south, the patterns of marine heat waves don't change. They do change. And actually, it doesn't mean that we don't have extreme temperatures. But in the case of AMOC off, we have extreme low temperatures. For acidification, what we see is that an AMOC shutdown is associated with acceleration of acidification of the Arctic Ocean. You can see here that the values are much lower of the concentration of negative ions in the ocean. Positive ions in the ocean. But in the case of the AMOC collapse, we have the concentration of them increases substantially, which means that pH is even lower. And that would have, of course, detrimental impacts for fisheries and also calcifying organisms in the area. We already know that the Arctic Ocean experiences intense acidification, but the extremes in the case of an AMOC shutdown will be very pronounced. So I'm finishing my talk here, which is a broad overview of the types of fingerprints that we see associated with an AMOC collapse, with some take-home messages. The first is that AMOC has profound impacts in the Arctic Ocean, in stratification, in fluxes, in sea levels, in biogeochemistry. The mediator of these changes is crucially the subpolar North Atlantic. What happens there will eventually get into the Arctic Ocean. We don't see as much effect from the Bering Strait coming into, although it does bring in some warm waters from the North Atlantic, but the amounts, the volumes are small enough that they don't make a difference while the climate is changing. This Atlantification that we identify here is opposite to what the conventional sense is of cooling and freshening, but it is showing how important is the subpolar North Atlantic to the Arctic Ocean. And also we want to highlight that the changes in the Arctic are climate state dependent. These fingerprints or these impacts, they are not necessarily going to be the same as if we had, for example, an AMOC shutdown under conditions maybe under, for example, pre-industrial or even current climate. These simulations that I showed you about is a global warming level of about 2 degrees. So maybe qualitatively they would be similar, but at least the magnitude of these effects would be very different. And therefore, the AMOC fingerprints are state dependent, and that's very important to keep in mind when we are looking to use fingerprints to identify possible collapse of AMOC. We can't use fingerprints which were determined in a pre-industrial climate to put them into the context of a current climate change or even future climate change and expect that they are evolving themselves and they are state dependent. And maybe they could have different regional or temporal characteristics. And thank you very much.
All right, thank you very much, Natasha. That's very, very interesting. We are over time, so how about people have questions for Natasha, please put them in the chat, and maybe if we have time at the end, we can revisit them. But let's move over to our next speaker, who's Andrew Roberts, esteemed colleague of mine at Los Alamos National Laboratory, who holds a PhD from University of Tasmania in Hobart. He's going to talk about the E3SM blue tip experiment.
Thank you. Can you hear me and can you see my slides?
Yes, that's great, Andrew. Thank you.
So I'm talking on behalf of the Energy Exascale Earth System Modeling Project, and specifically the Polar Group, many of whom are listed here, on the design of a critical threshold experiment focused specifically on the capabilities of one model. I recently shared at a conference of the American Meteorological Society that my first instance of being involved intimately with rapid changes in the Arctic was on a field camp in April 2007, when we noticed that sea ice was very, very thin in the Beaufort Sea, much thinner than we had expected. And it resulted in our runway shortening somewhat. And eventually we left our field camp using short field takeoffs with an aeroplane. That episode in 2007, we didn't know at the time, but resulted in a minimum least extent of Arctic sea ice that then precipitated a lot of work on whether the Arctic had reached a tipping point in sea ice extent. Bajeko-styled models had pointed to the possibilities of nonlinear thresholds, but later work with more sophisticated Earth system models suggested that it was just part of a linear change. So with that in mind, since then, there's been obviously a rapid progression of work on tipping points in the literature. This is now a frequently used term. And of course, at IARPIC seminars recently, you heard about modeling to comparison projects focused on that. I'm not talking today about any community effort. Instead, I'm just going to talk about the effort of one particular model and experimental design based around that model. And for that point, the definition of tipping points has expanded a lot since its initial use, which was really in reference to a complex adaptive system. So I'm going to be using the definition just today, the very simple one from Matthews, of a critical threshold beyond which a system reorganizes, often abruptly or irreversibly. And the experimental design is really based around the roots in complex system dynamics, and not anything further than that. So definitely not to do with impacts, as TipMip is also related to, or changes in ecosystems or anything like that. So we're just going to be talking about physical changes. The point that Stocker made here, I've got in grey, about typists and linearists is relevant to how we designed our experiment. So just as a brief introduction to E3SM. So E3SM, as I said, is the Energy Exascale Earth System model, and it's the flagship Earth System model developed across many DOE laboratories together. So it has some unique capabilities for the cryosphere. These include ice shelves in the Antarctic, so water flows underneath these ice shelves in these regions in panel C here. And it also includes unstructured meshes, of which there are only 2 Earth system models in the world that I know of, including ours, that include unstructured meshes. So unstructured meshes are useful because they add roughly about 50% extra degrees of freedom to a mesh than would exist for a rectilinear mesh. And so in the most recent incarnation of E3SM, version 3, we're able to get down to nearly eddy resolving scale for our ocean and sea ice. You can see it goes down to about 25 kilometers right near the pole and certain focal points on our mesh. So it's between 25 and about 28 kilometer resolution. Another useful feature of E3SM is that we also have wave sea ice interaction and wave attenuation due to sea ice, of which I'll talk about a little bit later. One feature of the unstructured meshes is that it creates a very realistic looking Earth. The coastlines look much more realistic, and bathymetry looks much more realistic. So E3SM is really squarely focused on seasonal to multi-decadal predictions. So we're specifically interested in things that are happening over just the next couple of decades and not really much further out than that. That said, that abrupt changes that could result 100 years from now may be the result of things we're doing right now on Earth, or occurrences right now on Earth. So another key feature of E3SM is that it aims to simulate Earth at exascale, so a billion calculations a second, and we're gradually drifting towards using GPUs and also artificial intelligence for increasing our ensemble count. So the current version of E3SM, as I mentioned, is about up to 30 kilometer resolution or higher resolution in the oceanic regions, 100 kilometer for the atmosphere and 0.5 degrees for land. But we are heading towards an eddy and cloud resolving target for version 4, expected to be released in 2027. So that's E3SM, and the important points I wanted you to know from that is the cryospheric capabilities, which are somewhat unique. One of which is in the sea ice model, which I'm going to elaborate on just after sharing our learning curve here. So it's taken some time to put together this sophisticated system model, and this is our learning curve. You can see that we weren't really hitting global Earth temperatures at mean surface temperatures until our most recent version of the model, version 3. So the black here is observations and the green is version 3. Previous to that, we had problems right across the model that we've been able to sort out, including in aerosols, in the simulation of sea ice and the ocean, and in the land. And gradually we've been able to resolve those issues to the point that we now have a model with relatively good veracity. So onto the experimental design is how one would design a critical thresholds experiment with a sophisticated cryospheric component in a model. I'll point out that the presence of ice shelves is something that very few models have. And so we thought it was important first to focus on how we would design an experiment just for our version of the model rather than trying to engage in too much modeling to comparison at this stage. That's not to discredit MIPS, it's just to say that at the moment, we really wanted to focus on the science of critical thresholds with this new capability. So Blue Tip is designed to be a pulse experiment. So that's not unusual, ramping up and ramping down of some trace gas in the atmosphere to find out what the impact is. But I think the main point here is what we would like to understand is the extent to which certain parts of the system could be nonlinear and other parts linear as a response to those trace gas changes. So rather than defining reversibility in terms of, say, carbon dioxide concentration in the atmosphere or, say, nitrous oxides, something like that, instead, we really want to stay true to the original complex adaptive system of irreversibility in the state space. And I've got an example here of for sea ice. There's a certain part of the state space with respect to planetary albedo that is never sampled in a model. And this was, in fact, the original driver behind some single column models suggesting that there could be tipping points in relation to sea ice. So our null hypothesis is that the system, the cryospheric components are linear time invariant. So an LTI system is easy to define in terms of this function here. So this is a convolution, straight convolution in terms of the forcing going into our system, which is just Earth, and we're going to consider this a speck in space. It has an impulse response function that produces a signal. Now, if our system is linear time invariant, that means that no matter what forcing we give and what signal we get, we'll have the same impulse response function. If it's nonlinear, the impulse response function will vary depending on the forcing. And that's a relatively easy test, and it can be done at both at the planetary scale and at the individual scale on the grid, at individual grid points. But I'm going to talk just for the moment about the planetary scale. And so for a pulsed experiment, in order to be able to do this, rather than just feeding an individual pulse, so the classic one that's been used in previous pulse experiment, especially for sea ice, is 1% increase in CO2 and a 1% decrease in CO2, looking at the response of the model. But in order to do this type of pulse experiment, you need many more than just one pulses, or at least several more than one pulse. So we are supplying the model with both a step function, 4 times CO2, 1% CO2, and 0.5 CO2. And on the right here, I'm going to blow this up so that you can see the point here is that if a system were linear time invariant, you could have a large lagged system or a small lagged system. So a large lag might be ocean heat content, a small lag might be sea ice extent. And if this were linear time invariant, they'd just have a single impulse response function. Here, I've just provided an artificial example. And the state response would look like something like this for these 3 different forcing functions here. But if you look at the changes, the state response with respect to CO2, you'll see that nothing's following the same path backwards and forwards, and you wouldn't expect it to. I feel that in previous literature, this point has somewhat been conflated with irreversibility, and this isn't true. So this is a completely reversible system. It's just that it follows a different path and has a very different shape with respect to decreasing and increasing CO2. And all that exists between the difference between these two is a lag. It's this impulse response function. So it's very important to think about reversibility in terms of the complex system, not just forcing, because that's not really a meaningful thing in a complex system. So on that point, we divided up EtherSM into 5 different configurations of the model where we would like to test the impact of different pulses of trace gases to different aspects of the model. Sea ice, marine ice sheet instability, basal melt under our ice shelves, wave sea ice interactions, and ice shelf mass balance. Ice shelf surface mass balance. And I'm going to focus first of all on the sea ice part and just go into a little bit more detail on that because that's the most progressed part of this experiment so far. So I'm going to blow up on the right-hand side. This is where we are for EtherSM version 3. We previously did not have a good sea ice simulation that was useful for an experiment of this kind. But as you can see from the green versus the blue curve here, so that's V3 versus version 2, we now have a plausible model that agrees on the right-hand side here with trends in observations. We do have too much sea ice loss in summer, but these are relatively minor biases as compared to the overall trend lines, which you can see match closely with observations. Even if it is a linear trend, I appreciate that's the lowest bar to hit here. We don't quite hit the bar for the Antarctic, but we're also mainly within the 95% range of the model. You'll note that the impact of aerosols influences in the 1940s and 1950s, the sea ice variability, and we actually have an increase in volume in the Arctic, up subsequent to quite a lot of volcanic eruptions during the 1950s. So that's sea ice in a nutshell. You can look at this in more detail if you were to run a satellite emulator over the model, and you can see that we don't quite have build up against the archipelago as compared to IceSat. We run a satellite emulator, so we create a synthesized version of IceSat in this example, just flying it through the model, sampling at the same place and time as observations. And as I mentioned, we have a significant bias in the autumn. But I don't think any of this discounts its use for a critical threshold experiment. You can still see that we have relatively healthy sea ice cover, even if we are losing too much sea ice at one part of the annual cycle. This is showing 1 year's simulation daily from 5 different ensemble members of the model. And you can see there's quite a lot of variability between these models, but on the whole, as you saw on that graph earlier, the use of ensembles isn't necessarily as important as the individual pulse experiments. And so we're not planning to run lots of ensemble members for the pulses, but instead just look at multiple pulses as part of the final simulations. Turning to the marine ice sheet instability. So we already have these simulations complete, and you can see this is flow under Antarctic ice shelves. This is the melt fluxes. Here as an example from the SSP 3.7 scenario here. And this is the flat line for the control, you can see. And output from this is being used by Matt Hoffman and a student that he's been working with to provide forcing to an offline version of Mali, which is an Antarctic ice sheet model using unstructured meshes that is in the process of being coupled to E3SM. But this is an offline experiment being used, and early results suggest this is still a very useful type of experiment to run as a force scenario. Moving on to the basal melt critical threshold papers, this is really the core part of E3SM. So we are very close to finalizing this model, which has a 12-kilometer resolved Southern Ocean region. So using the unstructured meshes, we're able to highlight resolution and thermally active ice shelves. The next part of the experiment is wave ice ocean nonlinearity we would like to test for. And on the right-hand side, you can see the unstructured mesh for WaveWatch 3 that Erin Thomas has worked a lot on with Steve Bruce. And we provide high resolution to allow for shoaling of waves in shallow water regions around the Antarctic. And this occurs on a different mesh from the blue mesh you can see here for the ocean model. And so those simulations are very close to being underway. Here I'm showing a significant wave height simulated for around about a year, where the waves are attenuating through sea ice. So you can see the wave height decreases a lot where there is sea ice. And there is active flow size here, and the flows fracture. And so the thing we'd like to know is, does this add any source of nonlinearity on top of the existing sea ice model that we have, which is relatively sophisticated? So we're using IcePack for the sea ice and then adding the flow size distribution here. We would also like to know how this changes wave heights close to ice shelves as a potential source of extra melting of ice shelves. And the last component of this is to include deep firn rather than snow capping in a model and understand if that adds any nonlinearity to the response of the model. So that is the blue tip experiment in a nutshell. So just to sum up here, blue tip is a pulsed tipping experiment. So we're testing again for linear time invariance and state space reversibility. And exploiting 5 E3SM configurations. So the sea ice includes this new IcePack model, so it has a snow morphology, sophisticated radiation physics, and a flow size distribution. The land ice includes thermally active ice shelves, deep firn, and data iceberg spreading, which I didn't mention, of solid freshwater fluxes from the Antarctic. And we've been able to establish the veracity of our model. So we compare pretty well with historical and using SSP 2 to or 4.5 to compare with observations up to the end of last year, December 2024. But the important thing is that the pulse experiments are not driven by any protocol. They don't need to be. All they need to be is different from one another substantially in their shape and their magnitude to test for this linear time invariance. So one of the features of this so far is that we do have total Arctic sea ice loss this decade in our model in 2 ensemble members. But as I've shown you, we're slightly too extreme in our summer extent. And so that's probably going to precede the real world. And our ice shelf melt rates are commensurate with a surface temperature. But there's no abrupt changes in one of the experiments I showed you there up to 2100. So we're finalizing these last 3 configurations of the model, and we're expecting to be complete by September. So with that, I'll take questions.
Great, thank you very much, Andrew. Very ambitious project. Thank you for presenting it to this team. So if you have questions for Andrew, please raise your hand and look on. I guess one question quickly, Andrew. Did you do actually experiments with the perturbation? I do not remember having seen that, the pulsed experiment.
That's right. You haven't seen it.
Okay.
So we've done the ramping so far, and so
Okay.
we end up with so ramping up, but we are rerunning all these experiments on a different machine. So that we do ramp up and ramp down right now. So, yeah.
Good, thank you. Hyle?
Hey, yeah, thanks, Andrew. That was very interesting. I've got a question more from a broader perspective of observational data. I recall that there's these continuing discussions about whether you're able to detect any transitions in system state, that correspond to a tipping point by looking at, autocorrelation of the time series, variance, et cetera. So from the work that you're doing, do you feel that you can help guide where observations of state of these different components of the cryosphere, say, would be particularly valuable, both in terms of region or the types of variables observed? Any thoughts on that would be interesting. Yes,
is the answer. So exactly how, that's the best answer is yes. So I think you may be referring to, there's been some work suggesting that, a complex adaptive system starts to generate wobbles just before it bifurcates. And so the question is, does that appear in a model? As an example, do we see lots of variability? So I think the Antarctic, you could argue that for the Antarctic, we're beginning to see all sorts of very high variability. The last 10 years has been more variable than the previous 25. And so we would be wanting to look for that, and we are trying to look for that in the model as well. Yeah.
Any more questions for Andrew or for Natasha?
I guess I have a question, Andrew. Have you guys thought about, or have you started to compare how the results look kind of more regionally as opposed to kind of more of a larger scale look? Like, do you anticipate kind of larger variances grid cell to grid cell as you try to look at these transfer functions, or do you expect to have to average over regions, or have you started to think about scale spatially in terms of how it's going to fit into this format?
Yes, is the answer. So I just shared the global, thing of the Earth as a speck in the space, and treating a whole Earth system as a one-dimensional model, which is not doing it justice. But regionally, you can do exactly the same thing of having impulse response function for every single grid point in your model. And so you can look at a regional response. And there is a paper that's just come out showing that the that sea ice loss, as an example, is linear on a global scale, but that's not necessarily the case regionally. And so you looked at Natasha's talk just now. There is a distinct regional signature, and so that's one of the advantages of applying this type of LTI filter on everything, is that you can do both.
Great, thank you.
We can also open it up to a little broader discussion. And I guess one question that I have for the rest of the audience: are there any other activities going on in this space of tipping points that we're not aware of and that maybe we could highlight at some point? And feel free to speak up later or to put in something in the chat. Natasha, I have a question for you. I thought it was interesting to see the freshening in the high latitude Atlantic Ocean with the AMOC off, and it was associated with a weakening of the precipitation.
Yes.
Yes. But was it the evaporation that kind of dominated the signal over precipitation?
So both weaken. The precipitation weakens, which would lead to salinification of the surface, but also the evaporation weakens, which means freshening of the surface. And then the overall effect is actually the evaporation reduction is larger than the precipitation reduction, and that's why we end up with more freshwater input into the surface.
Okay, and the advection of or the lack of advection from lower latitudes plays a key role. You're saying.
Yes, plays a very key. Yes, I think this is the dominant term for the lower salinities. Obviously, not only at the surface but also at depth. And so the water down to the 1,000 meters is fresher, and that is definitely advection associated with the large-scale ocean circulation, which is slowing down.
Great, thank you for the clarification. David?
Thanks. This is a question for Natasha, and pardon me if I missed it during your talk, but I'm curious about impacts on, say, the East Coast of the United States in terms of, for instance, sea level rise or the position of the Gulf Stream, and whether or not there's a larger difference between the AMOC on, AMOC off, or the the variance within the ensemble of AMOC on cases.
Yes.
Can't say anything about it. I don't know.
Yes, yes, thank you about this. Yes, I focused mostly on the Arctic and left out really the eastern coast, the southern eastern coast of the United States. But indeed, AMOC shutdown is associated with very large signatures of sea level rise in the eastern coast of about 1 meter. And but as I explained before, as I said in my talk, that actually what happens is that this is an AMOC shutdown that happens at a 2-degree warming world. There's a lot of committed warming in the interior ocean that is being moved around with the circulation, and therefore a large expansion that has already happened in the system. The AMOC collapse exacerbates that, and so we reach levels which are about one meter. This is way larger than what we expect from other studies of AMOC collapse using freshwater inputs, but this could be biased because they don't have, as I said, the halosteric effect, which plays a big role in the colder parts of the ocean, and also this is usually these models always will have to modify the salinity to keep the simulation stable. So I think that there is room to believe that this increase of sea levels is plausible when we have AMOC collapsing is slow, is a little bit faster than to what we are seeing right now, but not anything that's, if you take the scales of 200 years into account, it's plausible. Thank you for the question.
Richard?
Hi, Natasha. So you showed simulation results with AMOC on and AMOC off, but I would assume, of course, that there's a transient period both for the AMOC and for the response, the Arctic response to the AMOC off. Can you characterize what time scale is expected for when the AMOC turns off to a response in the Arctic?
Yes, I haven't looked at that, but it is an interesting question. Actually, while I was putting together this presentation, I thought that it would be very interesting to see the timing of each of these fingerprints. How quickly do we see the setup? We know that the salinification happens pretty quickly. The Atlantification of the Arctic Ocean happens pretty quickly. But for example, the other effects and the buildup of sea ice obviously at the surface, but other effects, for example, how quickly the stratification of the Arctic changes. I would be very interested to see that time scale, how quickly it evolves. Yeah.
Okay, thanks.
Thank you.
So we're getting to the top of the hour, but there is an interesting thread started in the chat. Twyla, would you mind speaking up? We had a discussion at our previous tipping point session as well about the communication of tipping points, and I remember that you had some insightful thoughts about that.
Yeah, well, and I appreciated how putting a note in there about just how we communicate about this. You know, in this case, pointing out that the polar places and cryosphere has so many connections to things that get discussed in this framework. But as we had talked at that earlier meeting, that we also have to be mindful maybe of the problematic parts of that framing, which are really brought up by this COP article. But then I was just reading today, it came out a while ago, but it took me a while to get to to reading it, was a letter that was responding to the COP article about the benefits of how we talk about and think about tipping points. So there's really is a lot to unpack there. And it could be really, I think I agree, interesting conversation for our community and for thinking about how we talk amongst ourselves and how we present things in publications or talk outside of the research community.
Mm-hmm.
Very great, thank you. So we are at the top of the hour. Let's thank Andrew and Natasha again for their very insightful presentations. It was a very nice session again. I'll hand it back over to Hazel to close things up.
I think I just put a couple links in the chat where folks can find the recording and make a IRPRIC collaborations account. If you don't already have one, make sure you've joined the Modelers Community of Practice to stay tuned for all of our future meetings. Richard, do you want to say anything about upcoming meeting plans, or folks should just tune into the email?
We are planning a next meeting on a slowdown in the trend of September Arctic sea ice. So that meeting is still in the planning, so stay tuned.
All right. Thank you all. Really good to see you all today. Thanks for the great discussion. And thank you especially, Andrew and Natasha.
Thank you.
Thank you.
Thank you very much.
Bye,
Bye, everyone.
everybody. Bye-bye.